All right, so welcome everyone to this seminar on Modifinder. So this is a new tool in the GNPS2 infrastructure that was just recently submitted. So maybe this tool is new to everyone, or maybe not. But presenting this tool will be one of the developers, and this is Reza Shahneh, and he comes to us from Ming Wang's lab at UC Riverside. Now, he's a fifth-year PhD student. Before joining Ming's lab, he has a background in theoretical machine learning, but now, of course, he works in computational mass spectrometry. And also prior to joining UC Riverside, he was at the Sharif University of Technology in Iran. And so, yeah, we're very excited to have Reza here with us to tell us about the new tool that he has developed. So the floor is now yours, Reza. So take it away.
Thank you so much for the introduction. And I'm very happy to have this chance to present Modifinder. Let's start talking about this new tool. All right, so first the problem setup. So the problem at hand is identification of small molecules in a sample. And one of the tools we have is to use tandem mass spectrometry. It is a very powerful tool. It is fast, reproducible, and provides structural information about the molecule. However, most of the MSMS data set we have at the moment is contained by unknown entities. This is, on average, more than 87% of all the data gathered. So understanding the structure from MSMS data, it's not impossible, but it is not easy as well. So how do we go on handling this issue? So first of all, molecules don't appear in isolation in nature. So we can use library search or create a molecular network out of molecules that are similar to each other, and then try to analyze the compounds based on their similar molecules. However, molecular network itself cannot determine the structure. It can only determine the similarity between two compounds. So here is where Modifinder is developed to predict the location of modification from a known molecule to its similar analog. So this is not a completely new approach. It has been looked at before in proteomics for post-translational or chemical modified peptides. However, these two spaces are completely different in a sense that a small molecule is a graph space, whereas whereas proteomics is just a string space, and graph structure is obviously a more complex space than a string. So let's talk about the problem setup of the Modifinder. So as input, Modifinder accepts an MSMS data and the structure of a known compound, and also the MSMS data of an unknown compound. And then as its output, it tries to predict the location of the modification. So first, let's talk about the intuition of how this process is done. So imagine that we have two compounds. One is, both are structurally similar to each other, and we also have the MSMS data of both of them. So the first step is to align these two MSMS data. So we know that bounds of structurally similar compounds don't change in their behavior when they undergo the fragmentation process. So many of the same fragment ions appear in both of these MSMS data. And we can align these fragment ions together. So for example, here, if we annotate these peaks, and this is a toy example, this is just for demonstration. So if we annotate these peaks, we can see that this same peak appears in both of the MSMS data. Because similar fragments have the same weight, and here is this example on a real world where these two fragments appear in the MSMS data. So there are peaks that are shifted in mass. That is, there are peaks that in the first compound have a weight, and then on the second compound, they have the starting point, but also have that modification in them. And the difference in the difference of precursor mass is actually the mass of this additional part. So here we can see two different structures, and this part they differ by the modification. So if we look at these fragments that contain the modification site, for example, here the blue one corresponds to one of these shifted peaks, and the green one corresponds to another shifted peak. And if we look at all these fragments, then the intersection of these fragments is likely to be the modification site. So how do we plan on changing this? How do we plan on making a tool that uses this intuition? So the first step is to find the annotations for the peaks. We use in silico fragmentation tools. So our algorithm is here based on the Magma algorithm. And the way it works is that it starts from just having the whole structure. And on each step, it just removes one of the atoms from the structures and see all the substructures. So here, A is removed, and then the remaining substructures is added to the set S prime. And then second atom is removed, and this process continues until, and this process continues until we have all the substructures. And then the weight of these substructures are calculated, and the peaks are annotated based on these weights. So here is this example, and the peaks are annotated with the substructures. As you can see here, one peak can be annotated with multiple different substructures. So also this is the root reason that this method by itself is too general and ambiguous, because too many substructures can be assigned to each peak, and each atom can essentially be in all the different peaks, and therefore calculating the intersection between these would not result in a good prediction for the modification site. So the first step we do is to improve the annotation using the series tool. So that tool provides the formula for each peak, and therefore we can filter some substructures that don't match with this formula. For example, here, after doing this filter formula, we then end up with having a few substructures assigned to a peak. The second way we can use data to improve the ambiguity in our annotations is to use helper compounds. By that, we can take advantage of other structures in the data set that have similar structures to the known compound. Here, we can see that we have our known compound and another known compound in the data set referred to as the helper compound. And we have both of their MSMS data. So if we perform the alignment again for these two compounds that we know both their structures and MSMS data, then we can see that for the shifted peaks, the peaks that are shifted in mass, we need to have the modification sites in those peaks based on the intuition discussed before. With this in mind, we can remove some of these annotations. For example, this orange substructure assigned to this red peak here, it is going to be filtered because it does not have the modification part attached to it. So this way we can again reduce the ambiguity in our substructures and annotated to each peak. All right, so that's the first step. Once we have the fragmentation and we have the annotations assigned to the peaks, then we need to find the alignments. So the way this works is for each peak, they can be either shifted with the delta, which is the difference in precursor masses, or they can remain the same. However, this can take an exponential time because each peak can be either shifted or not shifted, which means we have 2 to the power of n, assuming we have 2 to the power of p, assuming we have p peaks. So and this is an example of these assignments. So the peaks can be shifted or not shifted, and there are many possibilities. This algorithm is extremely slow, as the number of peaks can be in the orders of hundreds. However, there is an algorithm that does this as an approximate, of course, using a greedy algorithm, and it has been developed in the GNPS, and this is the alignment algorithm that we're using. Here you can see an example of the alignment between the 2 compounds we were discussing. So red ones, they highlight the shifted peaks, and the blue ones, they highlight the unshifted peaks. And the gray ones are the peaks that are not necessarily matched with our alignment algorithm. All right, so once these 2 steps once we have the fragmentations and also the alignment, it is now time to calculate the likelihood score for each atom, which means it is time to calculate which atom is the likely location for the modification. Okay, so we introduce 2 different scores. The first one is the contribution score, and that is how much each atom contributes to each peak. So this is shown as theta, and it is calculated as follows. So for each peak, we check all the annotations that have been assigned to that peak, and then each atom that exists in those annotations is going to be added 1 contribution score. The second score we calculate is the clarity score, and that is how much a peak is going to be informative. And it is based on the Shahneh entropy formula. So this is just going to look at the contribution score and calculate the entropy for that. Finally, when we have that, we calculate the likelihood score based on these 2 scores. So just to make things clear, because I know formulas don't necessarily map to anything, we have an example to show this. So here we have the alignment. I'm sorry, this is sideways, but to have all the data in one figure. So here the 2, here you can see an alignment, and then each of these dashed boxes are the annotations assigned to the peaks. So the first one here, we can see that these 2 highlighted red parts are the substructures assigned to this peak, and the peak 56.05. And here we can see that the contribution score is shown as the color part. So the red ones show a more contribution score, and the blue one show a less contribution score. Here you can see that these 3 atoms, they show the highest contribution score because they exist in both of the possible annotations to that peak. And then the contribution score is relatively high because the entropy is the entropy is basically the focus is on a small part of the compound instead of having a, a, a probability setup that is scattered throughout the whole compound. On the contrast, if we look at the last one, we can see that almost all the atoms in the structure have a relatively similar contribution score, and therefore the clarity score of this peak is low because it is not that informative. So once we have the clarity score and contribution score, then the likelihood score is calculated this way. So if you remember the intuition, shifted peaks, they were likely to contain the modification site. So for each atom, its contribution times the clarity score of the peak is a positive reward for that atom being the modification site. And then for the unshifted peaks, it is the same score is calculated, but as a penalty. So here, if we look at the section E in the figure, it is the final result after Modifinder calculates all these scores and applies some other filters. So here you can see that at the end, this atom here has the highest likelihood score, and the rest are relatively lower. Which again corresponds to adding or subtracting all these values. So here in this specific example, the red dashed boxes are shifted peaks, so they are added as a positive score, and then the blue one is added as a negative score. All right, so to evaluate our method and see how good it works, we have used libraries in GNPS, specifically these 4 libraries described here. However, there is a challenge here for the evaluation part. And that is to say there is a conflict of interest because we have to provide the evaluation method while we are also providing the algorithm ourselves. So the reason this happens is that, so if we have the ideal algorithm that always works, then it would be great. However, that is not possible. The first issue is ambiguity might exist. For example, if the moiety part falls first, then we won't be able to see any informative data in the MSMS. So there's no specific data to help us figure out this part in the actual MSMS. The other issue is that our algorithm is not necessarily perfect and could have flaws. So it might not be able to assign the highest probability to the correct modification. And therefore, we need to have a more relaxed evaluation method. So because this makes us have this like conflict of interest, as we're trying to provide a more relaxed evaluation method, and we're also the one who provides the algorithm, we try to implement, first of all, a few evaluation systems and evaluate the performance of Modifinder in all of them. And also, we try to make the most sensible evaluation scores and not make them too complex, just to make things more clear and transparent. So for each likelihood score that we provide an evaluation method. Here it's called the score, and it has to be more close to 1 if the likelihood array is a good likelihood array, and close to 0 if the likelihood array is a bad likelihood array. So the first one proposed here is to provide 1 over the number of values in the array that are equal to the maximum value. So basically, this means, are we predicting the true modification site as the highest likelihood value, and also if we are, how many of these are we predicting? If this was only a 1 and 0 setup, then the algorithm could have learned to always predict the same value for all the atoms in the compound, and therefore always predicting the true modifications as the maximum value. However, this is not informative. So we added this like 1 over the number of maximum values just to make things more sensible. The second one is how close is our prediction value to the actual modification side. Here phi is the diameter of the graph, and we're calculating how close is our predicted value to the true modification side. And then we normalize that again by the diameter of the graph, because otherwise small compounds could have scored higher relative to bigger compounds, even though the algorithm was working better on the bigger compound. And then the last one is basically a combination between the two, and it's the average distance, and it calculates like the score times how far away that specific atom is from the true modification side. So when we evaluate Modifinder on the different 4 libraries and on the different evaluation methods, we can see that Modifinder is outperforming the random baselines, random DRC and RD, and the CFMID benchmark, which I'm going to talk about in the next slide. But here the takeaway is, regardless of the evaluation method, when we look at Modifinder against the baselines, we see that Modifinder is outperforming in every scenario. So how we did the CFMID benchmark? So the data set was made as follows. We assumed that we have the known structure, and also we know the modification. So generally, we don't have this information. However, for this evaluation part, we wanted to see if, given the modification information, if CFMID is able to score better than our method. So given the known structure and also the modification, we permutated this modification around the known structure, and then used CFMID to predict the intensity, the MSMS. And then we compared these predictions with the true, the grand truth MSMS, which gave us an alignment score, a cosine alignment score. And then we use that score as the prediction of the CFMID method. And again, if we look back at the result, we can see that our method was able to outperform this CFMID benchmark as well. All right, so this was it about how Modifinder works. But for you and to use yourself, we have multiple ways of accessing Modifinder. So the easiest one is to just use the website. Here is the link, and I think it's gonna be available in chat as well. Okay, let me show you this in action. Okay, so once you go to the Modifinder website, you can input the USI, your USI values, and also the smiles of the known structure. You can select the ppm tolerance and also the adduct, and then set the Modifinder to work. So here I've included a few examples. And after adding these values, we can see the peak alignment and also the prediction. In this specific example, because I have the smiles, the structure for the second compound, it also highlights the modification. However, if in a real world scenario, we don't have this specific structure, then it won't predict that it won't show that part, and it only shows the prediction. So one good thing about this whole structure is that the way we are annotating the peaks is that we are using the Magma algorithm. However, it is not necessarily the best way. I'm sure people, chemists here, have way more knowledge than like an in silico fragmentation tool. And because of that, and because this tool is ambiguous and it's not the best possible annotation tool, we have provided this ability for you to modify these annotations and therefore achieve a better result. So here you can see the peaks, and when you click on each peak, it shows you the substructures assigned to that peak using our annotation algorithm. So given that you have enough information about this, you can select which of these peaks is the correct one. In these specific examples, if we choose the peak 133, then we can select the substructure we think is more likely. And after applying this, Modifinder updates the value and also updates its prediction. So this way you can refine the substructures based on your own internal knowledge of the fragmentation. And Modifinder can immediately update its prediction. Okay, so the second way you can use this is going to be available as a workflow. It is in the testing setup. We already have everything implemented, and we're just testing everything, so it should be available very soon. But the way it works is you can just pass in a CSV file which contains multiple sets of known USIs and structures, and also unknown USI. And once that is done, Modifinder would the workflow would give you an output like this, which shows the USIs and the smiles and the prediction. And you can also click on this link provided here to go to the website and modify the peak annotations based on your own knowledge of the structure. It is also available in the library search workflow. So once you run your library search workflow, you can just click on search result, and then on the table there is a link to Modifinder. So you can click here, and then it takes you back to Modifinder with these inputs already added to the Modifinder. And lastly, you can use that in the molecular networking workflow as well. So when you visualize your network and click on an edge, you can scroll down and see the, I'm sorry, you can see the Modifinder link out there as well. So for each edge in your network, you can just go out and check that edge in Modifinder. It has already all the inputs you need added to the website, and you would be directly transferred to the correct setup. Thank you so much, and I'm available if you have any questions.
Awesome. Thanks so much, Reza, for this very detailed introduction into the background and showcase of Modifinder. I guess the room is open for questions. So if you just want to raise your hand or just unmute yourself, you can go ahead. I'll stop the recording in a second. So yeah, this part won't go on YouTube. Yeah. So yeah, to all of you taking off or watching this, thanks a lot for stopping by, and we'll continue with the questions in a second.